Hi, this is Dr.I.Sharath. I'm currently working as an associate professor and a head of the Department of St. Peter's Engineering College, located at Hyderabad, Telangana. It gives me immense pleasure to be a part of this sixth I2CT, that is International Conference on Convergence in Technology, which is technically sponsored by Mumbai section, IEEE Mumbai section. I have a professional experience of around 15 years, and I have recently awarded PhD degree from Geetham University, Vizag in the year 2020. My research interest lies in the field of VLSI and signal processing, and I'm a lifetime member of professional bodies like IETE and ISTE, and also the member of IEEE. I do have around 12 publications under my name, and I'm happy to be a part of this I2CT. Thank you. With this short introduction, now I would like to start my presentation. Before that, I would like to share my presentation with you. First of all, I would like to welcome all the participants and the session chair who's evaluating this presentation. As said, I'm very happy to be part of this sixth international conference of for convergence in technology, which is technically sponsored by IEEE Bombay section. My paper ID is 803, and my paper title is Design and Implementation of CORDIC Algorithm using Integrated Adder and Subtractor. The corresponding authors of this particular paper is Professor B. Srinivasu. He's another author, the co-author of this particular paper, who is also working as HOD of Department of EC at Shreyas Engineering Institute of Engineering and Technology, Hyderabad, Telangana. I would like to present the outline of this presentation. First of all, I would like to start with the background of the algorithm that I would like to discuss, and also what has motivated us for this particular research and what is the problem behind this particular paper. And I would also like to have a short light on the methodology that what we have adapted, and the literature survey that what we have conducted, and the research objective of this particular paper and the proposed solution, followed by the results and the conclusion, the future scope. And I'll end this presentation with references that what we have looked out for. Coming to this background on CORDIC algorithms, CORDIC, by the name itself, it suggests that it is an algorithm which depends upon this coordinate rotation digital computer. It was first described by J.E. Wolder in the year 1959. And in 1971, John Walther presented a unified approach for this CORDIC algorithm. It is one of those popular shift and add algorithm used to calculate many arithmetic, logarithmic, trigonometric, hyperbolic, inverse trigonometric function. It is very simple and iterative convergence algorithm that reduces complex multiplications, greatly simplifying overall hardware complexity. It has become a usual choice when the designer looks for a compromise between the hardware required and the latency. Therefore, it is actually used in many diversified applications in the fields of signal processing, and it is also used in the calculation of discrete Fourier transforms like fast Fourier transforms, discrete sine and cosine transforms, Householder transforms, etc. With this short background, now I would like to just give you an introduction about the CORDIC algorithm. CORDIC algorithm actually operates in two modes. Here I would like to discuss one of those modes where actually we do consider a particular Q naught where it has a coordinates of x naught comma y naught through which can be rotated through an angle theta. And once the after final rotation of angle theta, it reaches a particular coordinate point which is Qn, which is equal to xn yn. Actually, this Qn can be achieved by a matrix product where R is a rotation matrix, where R when multiplied with the Q naught, it actually gives us Qn, Xn comma Yn. Here the matrix product is a matrix that what we have identified in order to find the product with Q naught is R is equal to cos theta minus sin theta, and cos theta. This was first proposed by Wilder, and therefore when Q naught is multiplied with R, the product actually gives you the values of Xn and Yn, which comes out to be X naught cos theta minus Y naught sin theta, and Yn is equal to X naught sin theta plus Y naught cos theta. To achieve this simplicity of hardware realization of this rotation, the key ideas used in implementation of CORDIC are to decompose these rotations to a sequence of elementary rotations and then to avoid those scaling parameters. Here, in order to rotate from Q0 to Qn, we try to follow different rotations based upon some elementary rotations. I would like to explain those modes of operations as previously discussed. There are two operating modes. One is the rotation mode and the other is a vectoring mode. In the rotation mode, a vector Q0 is rotated by an angle of theta to obtain resultant vector Qn dash, and the direction of each micro rotation depends upon that scaling factor Zi. Whenever Zi is greater than or equal to 0, sigma I, the scaling factor is considered to be 1, and whenever Zi is less than 0, then generally we consider sigma I is equal to -1. And the vectoring mode, in this mode, a vector Q0 is rotated towards x-axis so that the component of y becomes 0, and the sum of all micro rotation angles becomes the angle of rotation of vector Qn. In this mode, the direction of each micro rotation depends upon yi, whereas yi is going to be some intermediate vector. The hardware architecture of the CORDIC iteration is generally given by this particular structure, where you could see that xi plus 1 and yi plus 1 are going to be the intermediate vectors which we obtain by elementary rotation, where sigma I represents the scaling factor, and this is how where sigma I can be plus or minus 1 based upon the rotation. Whenever we move forward, we generally consider sigma I is equal to 1, and whenever we move backwards, we generally consider sigma I is equal to -1. And 2 power minus I, it is actually dependent upon the values of cos theta and sin theta. Whenever I take this cos theta common in both of this can be represented with an angle of tan theta, and the tan theta is represented as 1/2 whole power I, which is written as 2 power minus I in this case. And the drawbacks of the CORDIC architecture are, the major drawback of this traditional CORDIC architecture is, whenever we would like to perform the computations, they are inherently sequential because of those two reasons. Firstly, the micro rotations or the elementary rotations that are performed on the intermediate vectors generated during this previous rotation. Secondly, in order to start the next rotation, that is the I plus 1th rotation, we require the value of the scaling factor, which will be depending upon the previous iteration, that is the ith iteration. Therefore, Garrido et al. Garrido and other mathematicians, through their work, has presented a new version of CORDIC and called it as CORDIC 2, and they subdivided the rotations into different angle sets. They were successful in showing their results that their work uses very few adders when compared to this previous work till date. Therefore, what are the basic angle sets Garrido and all the other authors has used in their paper? I would like to discuss those particular angle sets that what they have used. The first one is the friend angles, a set of angles alpha I for which there exists a set of coefficients pi is equal to ci plus j into si with angles of alpha I whose magnitudes are the same. Generally, where magnitude of pi and pj are going to be the same, however that alpha I is going to be a little bit different. In such case, I would like to give you a small example where the complex numbers with respect to p1 and p2 are generally shown as 7 plus j and 5 plus j5. Here, the magnitude of p1 and p2 is the same, that is square root of 5 square plus 5 square, that becomes square root of 50. In both the cases, the magnitude of p1 and p2 is the same. However, the angles with respect to those vectors is generally equal to 8.13 in the first case, whereas it is 45 degrees in the second case. But however, their magnitudes remain the same. That is the reason we call this P1 and P2 with all such kind of vectors whose magnitude is same, but their angles are different. We call them as friend angles. And the second set of angle set is defined by this authors is uniformly scaled redundant CORDIC. USR CORDIC uses the same rotation angles as the redundant CORDIC. However, all the angles have similar scaling in this case, and PV0 is generally, once again, the basic vector is generally represented with the magnitude of 2 power 2k minus 1 plus 1, and P1 is equal to 2 power 2k minus 1 plus j into 2 power k. It can be observed that the magnitude of P0 and P1 is almost the same, where P0 square will be always equal to P1 square plus 1. Therefore, those particular vectors whose magnitude differs by only a unit value, generally we identify them as uniformly scaled redundant CORDIC. Here in this case, alpha naught is equal to 0 and alpha 1 is equal to tan inverse of 2 power minus k plus 1. And I discussed some of those examples with respect to USR CORDIC rotators, uniformly shift redundant CORDIC rotators for different values of k. Here the values of k considered are from 1 to 8. The values of P0 are generally considered to be as said 2 power 2k minus 1 plus 1, and P1 is equal to 2 power 2k minus 1 plus j into 2 power k. Based upon those values, P0 is given as 3 and P1 is equal to 2 plus j2. And similarly, P0 is equal to 9. And in all these cases, the value of those rotation angle is equal to 0. Whereas in this case, it is equal to 45 in the first case, and in the second case, it is exactly half of the first case. And in the third case, it is 1 by 2 square times, that is 1 by 4th of this 45, and so on. This continues with a power of 2. Okay, it is a division of this 45 with a power of 2. That is the reason we show that it has 2 power minus I. P0 and P1 are generally, whenever the consider the magnitudes of P0 and P1, you could see in all these cases they are differed by only one unit value, that is equal to 1. And similarly, there is another angle set defined by Garrido et al. And they are called as nano rotations. Nano rotations refer to the kernel formed by the coefficient set pk is equal to c plus jk, where c represents the magnitude, real part, and k represents the imaginary part, where c is a constant, and alpha k is the tan inverse of k by c, that is the angle with which this vector is rotated, and pn is equal to c plus jn. This is how different kinds of nano rotations are formed based upon different values of alpha, and n is considered to be much smaller than c. This makes alpha k small and fulfills alpha k is equal to tan of alpha k. This leads to alpha k is simply equal to k by c. This is what these are the three angle sets that are defined in CORDIC 2 rotations, and based upon this, they have connected those rotation stages in 6 stages. First of all, started with this trivial rotations, and then basic rotations, that is from 0 to 90 degrees, 90 to 180, 180 to 270. And in the second stage of CORDIC 2 will be the friend angles, and stage 3 will be USR CORDIC, and stage 4 as a normal CORDIC rotation, and stage 5 also constitutes a normal CORDIC rotation, and stage 6 will be the nano rotations. You could see that whenever a particular vector is subjected to these all the stages, you will be able to see that the final angle will be somewhere around 0.580 degrees. Stage 1, in the first stage, it actually calculates trivial rotations by plus or minus 180 degrees and plus or minus 90 degrees to the set the remaining angle within the range of plus or minus 45 degrees. The hardware architecture is shown in this particular figure, which uses 2 negators and which is approximately equal to half an adder each and 4 2:1 multiplexers. These are the basic angles with which this trivial rotations carry out, and the coefficients are 1j minus 1 and minus j in this case, and the output vectors will be with respect to x comma y minus y comma x minus x comma minus y y comma minus x in all these stages. And in the stage 2, it consists of this represents the hardware architecture of the friend angles, which consists of 5 adders and 7 2:1 multiplexers, and calculate all the rotations of the kernel depending upon the configuration of the multiplexers. These hardware architectures are taken from this paper which we have discussed, And stage 3 constitutes ESR CORDIC, that is uniformly shift redundant CORDIC, and this shows the hardware architecture, and it uses 2 adders like the conventional CORDIC rotations. And similarly, in stage 4 and 5, we generally employ conventional CORDIC rotations. And in 4th and 5th stages of this CORDIC, to use CORDIC rotations by 1.790 degrees and 0.895 degrees. And in the final stage, we see this nano rotations, where the hardware circuit of the nano rotations is shown below. And it constitutes once again 2 adders and 2 multiplexers. This is how in CORDIC 2 rotation stages, generally in the paper, Garrido et al. Shown that they require a total of 16 adders and 21 multiplexers to actually perform these CORDIC rotations by using their algorithms, by employing different kinds of angle sets such as friend angles, USR, CORDIC, and nano rotations. And now, what made us to actually think in this particular direction is the high performance CORDIC architecture, as the architecture becomes a usual choice in the absence of hardware multipliers, and the limitations of the adders and the shifters which are used in this previous design, and the inadequate speed when implemented on software, and the great demand for implementation of the design on hardware in biomedical applications, and the diverse applications of this CORDIC algorithms lies in the fields of cognitive, radio, robotics, image processing, digital communication systems, which actually requires better designs of the architecture than that of the currently available research outputs. This made us to think in this particular direction and choose this CORDIC as an obvious choice. And the research problem that what we have identified is the redundant algorithms performs no rotation extension and affects the value of the scaling factor, thus making the algorithm data dependent. Therefore, in order to calculate those scaling factors for each rotation, which increases this computation time and hardware, therefore, these problems are addressed in our particular paper. And before discussing those objectives and the proposed solutions, I would like to also propose a literature survey. The literature survey consists of CORDIC implementation in various styles. The non-redundant and redundant CORDIC. These are the basic classification in which many of those authors has presented their CORDIC implementation in the literature, the survey, in the literature. Actually, a non-redundant CORDIC, once again, it has been implemented with Radix 2 architectures and low latency Radix 2 architectures in the years 1959 and 1989 and 2008. And similarly, in redundant CORDIC, we do have different implementations, starting with Radix 2, Radix 2.4, and Radix 4 in the year 1996 to the still date. And similarly, Radix 2 architectures are once again classified as variable scaling factors, constant scale factors, and based upon those prediction algorithms. Variable scale factors are proposed in the year 1987, whereas constant scale factors are still have improvements till date. And constant scale factors are once again represented based upon the sign digit arithmetic and carry save arithmetic, which has different levels of latencies and concentrated over high speed and bit level pipeline structures. And similarly, in the case of sign digit arithmetic, we do have double rotations, branching algorithms, deCORDIC algorithms, and double step algorithms, which are proposed till date. And in the case of Radix 4, we do have a variable scale factors, and we do have sign digits and carry save arithmetic, which are used in Radix 4 implementations. And the summary of all this literature survey that what we have conducted on CORDIC architectures can be briefly presented in this way. It has been developed to speed up the CORDIC blocks, reducing its iteration counts and through its pipeline implementations. This is what we have seen in most of those architectures, and the latency of the computation continues to be its major drawback, since we do not have efficient parallel implementations. It is actually suitable for pipeline design due to its iterative behavior, and for high throughput applications, efficient pipeline architectures with multiple CORDIC units can be developed. And research on fast implementation of shift accumulation operation, exploration of new number systems for CORDIC, optimization of CORDIC for constant rotation have scope for further reduction of its latency. With the enhancement of throughput and reduction in latency, it is expected that CORDIC would be useful for many high-speed and real-time applications, and the area delay accuracy trade-offs can be investigated for different advanced architectures. The research gaps that what we have identified in the previous work was the CORDIC 2 algorithms can be still improved for efficiency when implemented on hardware by dealing with efficient adders rather than using normal adders. And the binary shifting methodology can be improved for area and power savings. And the energy efficient methods like reversible computing can be used for designs of adders in order to improve the speed of the overall architecture. With these research gaps in our mind, we do have proposed a research objective, and the primary objective of this paper is to design an integrated adder and subtractor using this reversible gates for CORDIC implementation on various FPGAs families to enhance performance metrics of power, area, and speed. As proposed in the research objective, our objective is to design a integrated adder and subtractor using reversible gates. The binary full adders or subtractors that what has been used in the previous designs is only able to handle one bit for every input with the output carry and borrow of the previous less order bit positions. And if more than 2 bits are added or subtracted, then it creates an issue. Issue in the sense where it has been stalled and there is a decrease in this latency and all. And the reversible gates will overcome this problem and perform both the addition and subtraction in a single operation and produce the accurate output with the carry and borrow. Therefore, we are introducing reversible gates in our design. Reversible gates or those gates, it is a unique one-to-one mapping. If 2 inputs are given, then we obtain the same kind of output with respect to 2. And by implementing these logic gates, the gate counts, the garbage outputs, and the constant inputs are reduced when compared with the binary adder or subtractor. The reversible gate has mainly four types, namely Feynman gate, Toffoli gate, Fredkin gate, and Pierce gate. Those are named after their proposed authors. In our proposed method, we are trying to use Feynman gate and Pierce gate in order to build a integrated adder and subtractor. A Feynman gate, actually it is a reversible gate which is used to duplicate the required outputs. This gate is also called as controlled NOT gate, C NOT gate, and the input vector is and the output vector is something like this. The input vectors are x and y, and the output vectors are determined as x or x or y. The truth table for this reversible gate is given as x comma y and f comma j. As I said, it is a 2 input 2 output controlled NOT gate with the inputs having 4 combinations of 0 0 to 1 1 with the corresponding outputs to be 0 0 and 1 0. The Pierce gate is another reversible gate which we have employed in our construction of integrator and adder and subtractor. And the Pierce gate is a reversible gate which has 3 inputs and 3 outputs. And the input vector for this gate is x comma y comma z, and the output vector is p comma q comma r. In this gate, you could see that the truth table is clearly mentioned here, where it is also a 3 input 3 output gate, where the outputs is equal to x or y and xy XOR z. Based upon these 3 functions, we do have built this truth table for different input combination from 0 0 0 to 1 1 1. The integrated adder subtractor combinations, the design of this integrator adder subtractor actually contains 2 Pierce gates and 2 Feynman gates. And when we actually give a controller bit and a x input, we do provide 2 inputs x and y as coordinates for this particular gates in order to perform this integrator addition and subtraction. And the hardware architecture of this particular integrator adder subtractor quietly looks like this. We have actually replaced those normal adders in the stage 2 that what has been used in the previous work has been replaced here with this integrator adder and subtractors, and the architecture of these front angles looks the same when compared to the previous work. And however, where the normal adders, binary adders are now replaced with integrator adder and subtractors. And similarly in stage 3 also we have used integrator adder and subtractor in the place of normal binary adders. And in the stage 6 also we have replaced it with our integrated adder and subtractors. These are hardware architectures which looks after the replacement of this binary adder with this integrator adder and subtractor. And the top level schematic and internal RTL schematic of the proposed architecture is shown in this particular figure. And we do also have different kinds of results when implemented on different hardware like Spartan 3A, Vertex 4, Vertex 5, and Arctic 7. These are the various hardware, FPGA hardware we have used in order to implement our algorithm. The conventional CORDIC 2 algorithm, that is which was proposed in 3, as well as this RERO and LH CORDIC and the proposed CORDIC algorithms has been taken into account in order to have a comparison. And you could see that in the basic terms, you have the percentage savings in the area of 17.03, 13, and 4.45 when comes to this proposed CORDIC architecture. And similarly, you could also find some percentage savings with respect to 27.75, 24.22, 14.28 in the case of conventional CORDIC, RERO, and LH CORDIC. And similarly, we could also find some analysis of clock frequency, that what we have used with respect to our inputs, and the percentage savings with respect to this clock frequency is also shown with respect to the proposed architecture with respect to the conventional CORDIC, RERO, and LH CORDIC architectures. RERO is a architecture which is proposed by Ramados et al. It is also used for comparison and area analysis with 4 FPGA families, as well the power dissipation analysis and the frequency analysis is also shown with bar charts that what we have discussed in this particular table. And the contributions, the main contributions with respect to our particular paper is the number of adders and subtractors as well as shifters is decreased by this integrator adder and subtractor, and the performance of the proposed method is better in terms of area, power consumption, and frequency when compared with the existing techniques. And the simulation results also shows that the proposed method has improved performance characteristics when compared to these existing methods, and the overall performance of the proposed method is better when compared to the conventional CORDIC method. And in this particular work, we have used a pipeline CORDIC design, and to further improve the design, we have also implemented the architecture using the new integrator adder and subtractor, which was designed using reversible gates, and the number of adders and subtractors as well as shifters was decreased by using this new design. And the simulation results show that the proposed method has lower power consumptions of 27.75%, 24.22%, 14.28%, and a higher frequency of 42.43%, 23.99%, and 14.95% when compared with conventional methods, RERO methods, and the LH CORDIC algorithms, which were presented previously on an average. And also it has a lower area of 17.03, 13%, and 4.45% when compared to the conventional methods, RERO and the LH CORDIC algorithm respectively on an average with respect to the FPGA families. In extension to this work, the CORDIC algorithm may be used for high complex problems and designs like that of digital filters with low power and high speed. It can also be implemented for various DSP advantages and applications. And also there is a scope for improving the accuracy of the results in VLSI domain, and still various optimization techniques may be included to achieve better design performance. And the references that what we have used in our particular section was this one. I have considered all these 9 papers where I was talking about LH CORDIC and CORDIC 2, Mario Garrido and et al. And these are the conventional CORDIC architecture that was considered. Thank you for your patient listening. And if you have any queries, you can always post it. Thank you.